Okay, so in today's 2-hour lecture slot, I'm going to focus on one small fragment of the larger picture that we saw last week. So the larger picture was that last week I introduced you to many complexity classes. We had a whole range of complexity classes. Last week, we saw that the main complexity classes we've been looking at before, P, NP, well, were all contained in, this was polynomial time and non-deterministic polynomial time. If instead of time, if we look at space as a resource, we look at polynomial space usage, then in fact, everything, one of our main results last week was that everything in non-deterministic polynomial time can be computed in deterministic polynomial space. And then, of course, if we can have deterministic polynomial space, we've also got non-deterministic polynomial space. And everything in another of the main results last time was that everything in non-deterministic polynomial space can be computed in exponential deterministic time. Then, of course, there's non-deterministic exponential time. And so we had time, exp and nx, space, PSPACE and NPSPACE, time, P and NP, and there were some space classes below polynomial time, which was, we had the idea of computations only using a logarithmic amount of space in addition to their input. So the input, so a logarithmic amount of additional space, logarithmic of the size of the input. And that gave us non-deterministic logarithmic space, logarithmic space. So last time we had this big picture, and I want to focus today on a part of it. So let's rub off the parts we're not going to look at. They're not going to look at all at non-deterministic exponential time. We're not going to look at logarithmic space. We might do that next week. If you consider this chain of inclusions, from polynomial time through non-deterministic polynomial time through polynomial space through non-deterministic polynomial space up to exponential time. As I told you last week, does anyone mind if I close the door? We've got some windows open. So I told you last week, this is a strict inclusion. There are problems that require exponential time to compute that cannot be done, well, there are problems that can be done in exponential time that cannot be done, that cannot be solved in deterministic polynomial time. So this is strict. The amazing thing is that here we've got a chain of 1, 2, 3, 4 inclusions. No single one of these inclusions is known to be strict. None of the individual inclusions is known to be strict. I mean, we know that one of them is, at least one of them must be strict, but we don't know which one or how many. Except we do know one thing, and I already mentioned this last week, but this is a very surprising fact. The only additional fact we know beyond this is a very surprising equality. Well, surprising until you understand the reason why, then it's no longer surprising because you understand it. But anyway, this inclusion of polynomial space in non-deterministic polynomial space is actually an equality. PSPACE is known to equal NPSPACE. Exclamation mark, because that's surprising. But regarding the other inclusions, for any of them, it's not known whether or not they are strict. But in all cases, it is conjectured that they are strict. So it is conjectured, but we just simply do not know how to prove such results. So it is conjectured that all the other inclusions are strict. But none is known to be strict. But we do know that at least, so no particular one is known to be strict, but we do know that at least one is, of course, because P is strictly included in X. So that's the rather baffling picture that we have. What we're going to do today is we're going to really focus on this inclusion here, and then understand why it is an equality. We're going to do that using, again, the tools of the idea of completeness for a complexity class. So this was very important in the case of NP. Then we had the NP completeness, and SAT was an NP complete problem, and problems presented last week in the student presentations were NP complete problems. Well, some of them weren't. As was made clear, and today again we're going to have two presentations on NP complete problems. The completeness is a very important tool for understanding complexity classes, and today we're going to look at PSPACE completeness and also NPSPACE completeness. For today's lecture, actually, NP completeness is going to be the important fact we establish for a particular language that allows us to establish this equality. But still, given the equality between PSPACE and NSPACE, which we haven't established yet, but given that equality, when people are talking about polynomial space, people always just talk about PSPACE. Now, you never hear if someone is giving some presentation on maths that makes some allusion to polynomial space classes, people never talk about NP-space because there's an extra syllable involved in NP-space. It's more cumbersome to pronounce that. But everybody knows that P-space equals NP-space, so people just know the literature is full of references to P-space completeness. You almost never see NP-space completeness mentioned because it's the same as P-space completeness. Everybody knows that. We need to establish that, so we will need to work with NP-space completeness, but still for the title of the lecture, let's stick to the vocabulary that everyone uses. Essentially, we're going to be talking about P-space completeness. We're going to address this as follows. Well, we're going to prove that a particular language, a particular problem is actually we're going to prove that it's in P-space and it is NP-space complete. And this problem is an interesting mathematical problem. So just as we've been seeing interesting mathematical problems, that's SAT, for example, plus the problems that were looked at, that have been being looked at in the student presentations, we've been seeing interesting mathematical problems that are NP complete. We're now going to see the first of a collection of interesting mathematical problems that are P-space complete. And some more are again going to be presented in student presentations, not this week, but starting from next week. So this problem is going to be so the problem is called TQBF. And what this stands for, it's a bit like SAT. It's again to do with Boolean formulas. So BF is Boolean formulas. But we add something more to the Boolean formulas to make them more complicated than the propositional formulas we use for SAT. We need a harder problem because we've got a larger complexity class than NP. So we add something to the formulas, we add quantifiers to the formulas. So this stands for quantified Boolean formulas, and the problem is deciding whether a quantified Boolean formula is true or not. So T is truth of a quantified Boolean formula. And then what we'll show is that TQBF belongs to PSPACE, so it is indeed a PSPACE problem. And it's also PSPACE complete. But we'll show that it's so PSPACE complete would mean that we can reduce any PSPACE problem to it. But actually, we'll show more than that. We'll show that we can reduce any NPSPACE problem to the truth of the quantified Boolean formula. So in fact, we're going to show it's NPSPACE complete. Well, actually, hard, I think would be the right word. It is NPSPACE complete, but that follows from these two things. We're going to move it to NPSPACE-hard. And from that, as we'll show by a simple argument, it follows that hence PSPACE. If you don't see why that follows now, don't worry. There's going to be a little argument for this later in the lecture. And from this, basically from the facts above, it follows that PSPACE equals NPSPACE. So in doing this, we've proved this surprising equality, and at the same time, we found a nice problem that is a genuinely a PSPACE problem, and is even a complete PSPACE problem, is as hard as any other PSPACE problem. Right. Okay, so let's have a look at quantified Boolean formulas.
Don't forget you have two whiteboards.
Ah, fantastic. I started on the wrong one there, haven't I?
And the star.
Yeah. Thank you for reminding me. So next week I'll have to remember to start on this one, because you have to start on this one, and then because this one doesn't, I don't think this moves, does it? No. How did it, what's this one do with the Ward brothers? Well, so you don't mind me. I mean, we're hiding this now.
The buttons are there.
The buttons are there. Right,
That's
correct.
the remote time this a lot.
So, not being a physicist, I'm not. But this says, well, that's for the screen.
The black remote that's hanging, I believe. Maybe the yeah, the
This
black
one.
remote.
Oh, yeah, camera. Yeah, excellent.
You also go down.
Yeah, I was just thinking maybe this hides a bit better actually. Just you can probably see this. I can manage. No, maybe not. Right. Okay. Yes. So we were going to do. Probably good rehabilitation for my arm after the operation a few weeks ago. Now got to the stage, it's actually good to exercise it. So so this stands for quantified Boolean formulas. But let me first remind you, I mean, I know we've done this before. So formulas or formulae is What's the other? People often talk. There are two ways of pluralizing formula in English. It doesn't matter. This is the old Greek influenced plural. So let me write that because people, I think, normally talk about quantified Boolean formulae. But I'm not going to talk. So this is going to be quantified, but let me just, by a Boolean formula, I mean a formula of propositional logic, as we said. So, so a quantified Boolean formula is a Boolean formula is, as you'll remember, we're built from variables. So either it's a Boolean variable. So this is just what we had in lecture 4, I think. So Boolean formulas are the same thing as a propositional. It's the same thing as a propositional formula. So the kinds of formulas that we had the SAT problem associated with the satisfiability problem, which was the NP complete problem. So they're either variables or constants. We were using 0 false and 1 true. But then we had the ways of building new formulas. So if phi and psi are formulas, I don't really like the Greek plural, so let me use this one. And so are, well, as you remember, you can combine them by conjunction, disjunction, and negation. And I won't write out again what this means because we've seen that before. So these are what we call propositional formulas or Boolean formulas, because they're formulas over the Boolean truth values, 0 and 1, false and true. So a quantified one we simply add 2 new ways of forming formulas. So we can form them by existential quantifiers and by universal quantifiers, where we're quantifying over Boolean values. So we're going to quantify using our propositional variables over a Boolean value. So there exists a truth value such that, or for all truth values such that. So we have a formula. We can, so for any variable u, we can make the formula there exists a truth value u such that phi is true, and we can make the formula for all truth values u, phi is true. So this is there exists u in 0, 1 such that phi is true, and this is for all values of u, for all Boolean values of u, phi is true. This is called existential quantification. And this is universal quantification. Okay, so let's have a look at some examples. Excuse me. For example, here's a simple quantified Boolean formula. For all u, there exists to be such that u and either u and v, or not u and not v. So what does this say? This says, if we interpret this in English, it says for all truth values u So for all Boolean values of u, either 0 or 1, there exists a Boolean value of v. So again, there exists a v, either 0 or 1, such that the formula, which is now instantiated with zeros and ones as appropriate, depending on what value we're looking at for u and v, this formula is true. So such that u and v, or not u and not v. Now notice that this formula here, u and v or not u and not v, this is if we have values of 0 and 1 assigned to u and v, this is true, this formula, if and only if either both u and v are 1, in which case the left disjunct is true, or both u and v are 0, in which case the right disjunct is true. So this says, well, there's another way of writing this. This says u if and only if v, if you like, u and v, this is true if and only if u have the same value. We could even write it using an equality. Using an equality if you want. Okay, so hopefully that's clear to everyone. So if we look now at this for all exists, well, this statement is saying, so quotes, this statement is saying for all truth values for u, there exists a truth value of v such that this proposition holds. In other words, u equals v. Well, that's clear because we need to check it for all the truth values of u. So if u is 0, well then, of course, there exists a v that's equal to 0 because it's just v equals 0. And if u equals 1, then again there exists a v that's equal to u because it's just u equals 1. So hopefully it should be clear that this formula is true. Or if we like, if you want to keep on using 0 and 1 for true and false, its value, if we want to, we can assign a value to it and its value is 1. Maybe I'll try one of these other pencils. So consider though if we invert, oh that's worse. If we invert the quantifiers, so if we make it there exists a v such that for all u and v, or not u and not v. Now we're saying this formula is saying, I'm not going to write it out, but there exists a Boolean value such that for all Boolean values u, there exists a Boolean value v such that for all Boolean values u is equal to v. And hopefully that you can see that's false, because if v, well, there exists a value of v, it has to either be 0 or 1. So if v is 0, well, it's not true that all truth values u are equal to 0, because 1 is not equal to 0. And similarly, if v is 1, then it's again not true that all values u are equal to v, because 0 is not equal to 1. So hopefully you can see that this is false. And essentially here, well, this is a very simple formula, but the problem we are looking at here is, given a formula, is it true or false? Here we found out it's true, here it's false. It didn't seem very hard, so maybe it's actually surprising that this is going to be a very hard problem, harder than an NP problem. But let's have a look at why that's the case. So let's begin to relate it to SAT problems. So first, we notice that every propositional formula is a quantified Boolean formula. So the propositional formulas are just those formulas you build up using the blue parts without using any of the red parts. Okay, so it's immediate that propositional formulas are contained, are in particular QBFs, quantified Boolean formulas. So if we have a propositional formula, if phi is a propositional formula, so one without any quantifiers. So let's consider any propositional formula, the kinds we were looking at to decide whether they were satisfiable for the NP-complete problems. In general, such a formula will have some variables, and to be satisfiable, we're looking for some assignment of truth values to the variables such that the resulting formula is true. So suppose we've got k variables. And just to say, henceforth, I'm going to use the notation. I'll just write phi u1 brackets uk, say phi is a formula with variables u1 up to uk. I'll clarify that in a moment. And notice that we've been talking about the truth of a quantified Boolean formula. It doesn't really make sense to say phi is true, because phi is true or phi is false, because whether or not it's true or false will depend on the values in general, will depend on the values we've assigned to the Boolean variables. So that's why the questions for Boolean formulas are things like, is it satisfiable? Does there exist an assignment of truth values that makes it true? If you assign truth values, you essentially get a formula that's built without variables, because you substitute the truth values into the variables. And every formula without variables is either true or false. But for a formula with variables, it doesn't make sense to talk about the truth of the formula, but you can say satisfiable and you can say valid. The formula is valid, as we had in the previous lecture, if and only if under all assignments of truth values to variables, the resulting formula is true. But notice now what we can do is we can make these distinctions by adding some quantifiers here, quantifying over the variables. So phi being satisfiable, so phi is satisfiable, if and only if, well, what being satisfiable means is simply there exists some assignment that makes the formula true. So that's the same as saying there exists a u1, exists a u2, I just put dots, these are all existential quantifiers. So it exists the UK, so there exists an assignment of Boolean values here such that the formula phi is true. So we're saying, so phi is satisfiable, this is a Boolean, this is a propositional formula. We've now turned it into a quantified Boolean formula. So if this is true. So here, propositional formula. And here, this is a QBF. So we can see that the SAT problem is codable, easily translatable into deciding the truth of a Boolean formula. But similarly, the property of phi being valid can also be encoded as deciding the truth of the Boolean formula. In this case, to be valid is saying under all assignment of truth values to variables. So we simply replace the existential quantifiers here with universal quantifiers. And the validity of phi is asking if that formula is true. So we can see already that the truth of quantified Boolean formulas goes beyond the satisfiability problem, an NP complete problem, and also subsumes validity, a co-NP complete problem. And as you can imagine, if you start saying for all variables, there exists some variables such that for all variables, things can get quite a bit more complicated. So hopefully you get some feeling for QBF actually being quite a powerful formalism here. There's something important about these formulas here, which is all the variables in the formulas occur within the scope of a quantifier. So the formula phi had only the variables U1 up to UK, and here all those variables have been quantified, and also here all these variables have been quantified. So we have a name for such variables. So we've got an occurrence of a variable in a formula, such that this particular U here would be one occurrence of the variable U in this formula, and this particular U would be a different occurrence of the same variable U in the same formula. So two different occurrences. It's a standard English word, occurrence, and a place in which something appears. So an occurrence spelled two C's and two R's, an occurrence of a variable U in a QBF quantified Boolean formula phi is said to be bound if it lies in the scope of inside the scope of the quantifier. It lies in the scope of a quantifier of that variable. So either exists U or for all U. If it's not bound, it's said to be free. A free occurrence variable. So in this formula, for example, all occurrences in the variables are bound. We've got U occurs inside the scope of for all U, V occurs inside the scope of exists V, and so on. So the U here and the V here. If we take this Boolean formula phi as, if this propositional formula phi as a quantified Boolean formula without quantifiers, then all the variables in it are free, because there are no quantifiers to make them bound. Yeah, maybe. There's a simple example, just to illustrate these concepts. If we consider the formula exists a U such that not U and V and not W then we see that U is bound. The only occurrence of U, there's only one, is bound. And the occurrences of V and W are free. Because they're not inside any quantifiers for the variables V and W. So these are free. And notice that this formula is true. Well, to talk about it being true, we need to assign a value to V and W. Otherwise, we can't give it a truth value. So this formula is true. Is true if, well, for it to be true, we need to have V being true and W being false. So it's only true if V equals 1 and W equals 0. So if VW takes any other pair of values, then it's false. Because if V and W take any other pair of values, you can't make it true. In the case that V is true and W is false, well, this is true because it's true for there exists a U. It wouldn't be true with for all U, but there exists a U because U equals false will make this formula true. So what I wanted to illustrate here is that the truth of a quantified Boolean formula, so of a QBF, depends on and only on the values assigned, Boolean values assigned to its free variables. In order to be able to talk about the truth of a general formula, we need to assign truth values to variables, just as we did in the case of propositional formulas, Boolean of propositional formulas. We assign truth values to variables, and then we can talk about the quantified Boolean formula is true given this assignment of truth values to variables. So in particular, there's an important class of formulas that have no free variables. We'll call these the closed formulas. In first order logic, they're called sentences, but then first order logic is different in that the quantification is over elements of an arbitrary set, not over truth values. It's a bit different from first order logic here. So a formula, a QBF, a quantified Boolean formula, is closed if it has no free variables and if a formula has no free variables, then it's unequivocally true or false. So its truth would depend on assigning truth values to the free variables. There are no free variables to assign it to. So a QBF that has no free variables is either true or false. Just like those two formulas up here, the first two examples I gave, they have no free variables. So a closed QBF has a determinate truth value. And now, just to end, I can tell you what the TQBF problem is, but it's not really a surprise now, given everything we've said. So the TQBF problem. So the input is a closed quantified Boolean formula, a closed QBF, and the problem let's call it phi. The problem is simply, is phi true? So we don't need to look at, does there exist an assignment of truth values to variables that makes it true, because we don't have any free variables. Or for all assignment of truth values to variables, is it true? Because again, we don't have any free variables. And we can, that's no loss to us, because such problems can be coded up, as we did here with satisfiability and valid, and validity by adding quantifiers to the, in the appropriate way to the variables of the formula. Okay. And as a language, we want to define this as a language. Well, a language, sorry, as a language, we want a set of strings, but again, we avoid, as always, we kind of avoid saying what our encoding is. We just assume we've got some reasonable encoding of formulas and strings. So as a language, TQBF is the set of strings phi now, where phi is a closed QBF and phi is true. Okay, so it's bang on 9 o'clock by my watch. Well, it's like 1 minute past by the clock on the back wall. So we'll have a break now. We start again at 6 minutes past by the clock on the back wall. So it's just a short break for this one, this part. Let me pause the recording. Okay, so I've introduced the truth of a quantified Boolean formula problem. Is a closed quantified Boolean formula true? And the two main results about this are going to be, this problem is in polynomial space, so it is a p-space problem, and it is hard for NP-space, so it is as hard as any NP-space problem. That any NP-space problem can be reduced to. So the first one is the easier part. So let's just call this a proposition. It's not really a theorem. The proposition is that TQBF belongs to P-space. So we can decide this problem using only space that's polynomial in the size of the quantity closed quantified Boolean formula. That's okay. Is in p-space. So, to prove this, one could define the algorithm and quantify the space and so on. Actually, I think it's easier just to see it visually via an example, and then you can kind of understand why it's true. And if you want to wrap that up as a formal proof yourself, feel welcome to do so. So the proof idea, well, there are many ways of doing it, but the way I like to do it is like this. So I'm going to outline the algorithm. I'm going to illustrate. We're going to illustrate a p-space to decide the truth of a closed quantified Boolean formula. So let's take as input, in this case, formula we've already seen, which is true, because we saw that it's true for all u, there exists a v such that u and v, or not u and not v. And we saw that this was true, but how is our algorithm going to, in polynomial space, find out that this formula is indeed true? I think a nice way to see it is to write down the formula as what's called the syntax tree, in which we break down the formula into what is the outermost operation to construct the formula, and then what's it applied to, and so on. So here, this formula is a universal quantification over another formula. So this formula is the form for all u of there exists a v such that some inner, in this case, propositional formula is true. This propositional formula is a disjunction. I have to be careful to distinguish my variable v from the disjunction there. So let's make the disjunction quite big. Let's try and put a little tag on the v, a serif on the v. So this is a disjunction where the left-hand side is a conjunction. So that's an and. And here we have the variable u and the variable v. It's and of u and v. And on the right-hand side, it's again a conjunction of two negations. So here we have negations. And here we have u and v. Okay. And this tree takes up as much space as the formula to write down, or if we want to include to have it explicitly with pointers or something, I mean, we could make it take up exactly this space using a reverse Polish notation, but if we want to do it with pointers, we could, in any case, I mean, it's still linear in the space of the formula. So the tree is linear in the size of the formula. And onto this, we're going to add a certain amount more of linear space that we're going to use to calculate the truth of the formula. And what we do is, every time we've got a quantifier, we give ourselves two tape squares, each of which is going to take the value 0 or 1. And every time we have any other connective or a variable, we give ourselves one tape square, which is going to take the value u of 0 or 1. So this is additional, this is all the additional space we're going to use in our algorithm, in addition to the space for the formula. Also for the variables, for u, v. So we're decorating the formula by adding some additional space, padding it out. And the point is we're going to assign these things truth values, and we're going to use those truth values to calculate the truth value of the whole formula. The way it works, well, we want to see if this for all formula is true, so we just do the naive thing. But the point is we can do this in this space, which is linear in the size of the formula, because essentially, when we get to for all u, we want to check the truth of the formula below in two cases, u equals 0 and u equals 1. But the essential observation is, and it's a trivial observation, is we can check it for u equals 0 and then reuse the same space to check it for u equals 1. We don't need to make two copies of the space. And that's essentially all that's the main observation. So a very simple observation. So we start off, we want to do it for all u, so we start off with u equals 0. So here, this variable takes the value of u. And this variable is going to take the value of v. We want to do exist v, so it starts off with v equals 0. And now we come down to an OR. And to calculate an OR, we need to calculate the left side and the right side. So we go down the left side, we've got an AND, we need to do the left side and the right side. And actually, we should have done this at the time, but I mean, we can go back and check now, but we could have done it at the time we set the u. It doesn't matter. When we set the u to 0, we should write the 0 in all the places where there's the u. When we set the v to 0, we should write the 0 where there's the v. And now we can just compute backwards from the leads. U and v, 0 and 0 is 0. 0 negated is 1. 0 negated is 1. 1 and 1 is 1, 0 or 1 is 1. So now we get that to this particular value of the v equals 0, we've calculated the v equals 0 and u equals 0, we've calculated that the result of this formula is 1. We just need to find some v such that the result of the formula is 1. We found it, it works for v equals 0. So at this point, we can already write v equals what we can write the result of this is 1 here and go back to here. Now we calculated for all u, we're essentially doing nested for loops here, but we have an escape clause from an exist. As soon as we find 1, we can exit the for loop. So we've exited that for loop. We go back to the second for loop. We now see we've got a 1 as the result for u equals 0. But this is a for all. If we get a 1, we can't exit the for all loop because we need to check, we need to get a 1 for all values. If we've got a 0 here, we could exit the for all loop because that would mean that for all is false. Instead, we've got a 1 here, so we can't give ourselves the result value of 1 here. But we found that this formula is true for u equals 0. So now we change this to 1. We go into the next part of the for loop. The u becomes 1. Change the values of u below. And now we start this for loop to exist as v again. So again, we start with v equals 0. We wipe out all the values. Or we should have, whenever you start a new for loop, you should clean the tree below. I should have done that. So v is 0, that's right. So now 1 and 0 is 0. 1 negated is 0, 0 negated is 1. 1 and 0 is 0. 0 and 0 or 0 is 0. So now for this value of v equals 0, we get a false. So that was the first. For u equals 1, this was the first iteration of this for loop. We did v equals 0. We've got a false, but we can it could still be true because it might be true for v equals 1. So we need to check that. So now we go through the second iteration of this for loop and rub out the intermediate values. We change the v's at the bottom to 1. 1, 1, and then here we have 1 and 1, 1. Not 1 is 0, not 1 is 0, 0 and 0 is 0, 1 or 0, 1. So indeed, now we found that this formula is the existential statement is true. We got that for the value 1 for v, so we know we've finished this for loop, we've got the value 1. We go back to the top with the value 1, and this was the second, we were testing the second value for u here, so we knew that it was true for 0, otherwise we wouldn't have been at this stage. And now we can return the value 1 here, and this here is the result, true. Result. Okay. So, no, that was quite fast, but you can think about it for yourselves. The main idea is that every time we go through a for loop, we reuse the same space. That's really the main idea. You can think about it for yourselves as well. I just wanted to give you a kind of visual impression for how it should be done. So, So actually now I want to come to the main theorem today. TQBF is NP-space and this is due to Stock, Mayer and Mayer from 1973. I'll have that reference will be in the notes. I'm not going to write it down on the board. So firstly, what do we mean by NP-space complete? Actually, sorry, it is NP-space complete. What I'm going to prove is that it's NP-space-hard, hence complete. So let me just remind you of the definition, but it's not quite reminding you because I haven't given the definition for P-space and NP-space, but on the other hand, the definitions are pretty much exactly as you would expect if you're expecting the right thing. So you have to be expecting the right thing. I'll tell you just a little bit why you might not be expecting the right thing. So a language L, let's not write a language, so L is P-space-hard. If every P-space language is polynomial time reducible to L. So we have an algorithm for transforming, if you've got a P-space language, you have an algorithm for transforming strings over the alphabet of that language into the alphabet of L, such that the translation will be in the language L, if and only if the original string was in the language that we're reducing. We had the notion of reduction anyway, but if we can solve L using the translation, we can use our translation to use solving L to solve our language that we're reducing to L. So if every P-space language is reducible, but again we require polynomial time reducible to L. But the thing you might not have been expecting, you might expect, well, we used polynomial time because we were talking about polynomial time things before. Here we're talking about polynomial space. Why don't we say P-space reducible? Well, we could do, but then it would be a bit of a boring definition. You can think for yourselves why. But the idea in general is reductions. We want to make sure that reductions are always efficient things. So a reduction should be something we know how to efficiently compute. Whatever we're looking at, sometimes we'll have to make it even more efficient than P time, but somehow P time is always like the base, pretty much the baseline for the worst efficient. We want to make sure our reductions are actually efficient. And this leads to the rich theory that we have. So that's P-space-hard. NP-space-hard, well, we simply add an N here, and we add an N here. So to be NP-space-hard, it's as hard as any NP-space language. But we keep our reductions actually efficient in deterministic time. We don't want to add NP here because then we don't know if NP computations are efficient. So we keep here deterministic P time reducible. Okay, there's deterministic polynomial time. And L is either N or not, or P-space. In any case, definitions are going to collapse when we know that P-space equals NP-space, but it's NP-space complete if it is NP-space-hard. And it is also P-space or NP-space as appropriate problem. So the point of the ends in blue here is you either put them all in or you miss them all out, depending on whether we're talking about P-space or non-deterministic polynomial space. And in this case, if we've proved that TQBF is NP-space-hard, well, we've shown already that TQBF is a P-space problem. we know that PSPACE is a subset of NPSPACE because deterministic is always a subset of non-deterministic. So we already know that TQBF is a PSPACE problem, hence it's an NPSPACE problem. So then TQBF is an NPSPACE problem that is NPSPACE-hard, hence it is NPSPACE complete. It's also PSPACE complete because it's a PSPACE problem, and it's PSPACE-hard because immediate from the definitions is that any NPSPACE-hard problem is also PSPACE-hard, because there are fewer problems, there are fewer PSPACE problems to reduce to it. So if you're hard for a larger complexity class, you're always hard for a smaller complexity class. Okay, so hence it's complete, both PSPACE and NPSPACE complete. Before proving the theorem, which is, you're probably guessing is where the main work today is going to go. Before proving the theorem, I want to just outline, prove the corollary. Once we've proved this, we get as the corollary that PSPACE, the equality that I said at the beginning, the surprising equality that polynomial space is the same as non-deterministic polynomial space. So, assuming we've proved the theorem and proving the corollary given that, and this is, well, so what do we need to show here? We know that PSPACE is included in NPSPACE. We just need to show the other inclusion. So that L be a non-deterministic polynomial space language, we want to prove it's actually deterministic polynomial space. So suppose L belongs to NPSPACE. We want to give a deterministic polynomial space algorithm for deciding L. Well, because TQBF is NPSPACE complete, we can reduce L to the truth of a quantified boolean formula. So let's let F be a p-time reduction from a deterministic polynomial time reduction from L to TQBF. And what I want to show is that given this reduction, we can decide membership in L via a polynomial, a deterministic polynomial space algorithm. So then we have following deterministic polynomial space algorithm. Oh, sorry. I meant to say that, well, I don't need to write deterministic because PSPACE is deterministic. Anyway, the following PSPACE algorithm for L, and what is it? Well, I simply do two steps. Firstly, we compute F of so given an input word W, we compute F of W. And because it's a polynomial time reduction, so this is going to be it's a polynomial time reduction to we've got a polynomial time reduction to the truth of quantified Boolean formulas. So this is going to be some closed quantified Boolean formula. So this is a closed quantified Boolean formula, but this takes p time because our reduction was deterministic polynomial time, and hence if it's deterministic polynomial time, it can be done, hence it's automatically being done in polynomial space. Secondly, we decide if f of w belongs to TQBF. We decide if the closed quantified Boolean formula we get is true. This is PSPACE. So we've got two polynomial space algorithms. We apply them in sequence. First this one, and together we get a polynomial space algorithm. Okay. The main work to do is to prove that the truth of quantified Boolean formulas is PSPACE, is NPSPACE-hard. Is it okay to put the boards down now? Right, so we're going to prove that the truth of quantified Boolean formulas is PSPACE, NPSPACE-hard. So we can reduce in deterministic polynomial time any NP-space language to the truth of quantified Boolean formula. So it's going to be a bit like the reduction that we had for proving the Cook-Levin theorem that SAT is NP-hard. Similar kind of reduction, we're going to reduce a Turing machine computation now to the truth of a quantified Boolean formula. The thing we don't have in this case is we don't have, we do have a bound on the running time, it's exponential, we saw that, but that's not going to help us much because we want quantified, well, it is going to help us, but still at the end, we want our quantified Boolean formula to be only polynomial in the size of the input. So we're going to see how we're going to achieve that. So to begin with, suppose L is any NP-space language. If it's an NP-space language, it's decided by a non-deterministic Turing machine running in polynomial space. So suppose L is decided by an non-deterministic Turing machine M, whose space is bounded by a polynomial P of N, polynomial in the size of the input. It's an integer polynomial, natural number polynomial. So what we're going to do, as last week, we're going to remember the configuration graph that, given an input W, we construct the configuration graph of all configurations of this Turing machine N, possible configurations we can reach on this Turing machine N, starting with input word W. So this was something we looked at last week. So given an input word W, recall the configuration graph. which is a directed graph of M on input word W, whose vertices are configurations. You just write configs determined by, well, I wrote this down last week, but just to remind you, the state, so in any configuration, the Turing machine's in the state, it has its input tape, but its input tape always has W on it because you can only read the input tape. You have W on the input tape plus the tape head position plus head position on the input tape. And we have K words on the non-blank portions of the K working tapes. Plus K head positions, one for each tape. And that's all the information we have associated with the configuration. We start in the start configuration where everything's blank apart from the input tape, which has W on it, the heads are in the head on the input tapes in the relevant position, and the Q's in the start state, and we compute until we get into the accept state or reject state. And we have an edge between two configurations. I write this. From one configuration C, we have an edge to another configuration C prime, if and only if we have a single step of computation that takes us from one that can take us. It's a non-deterministic Turing machine. It might go in a different direction, but if it is possible for the Turing machine to go from this configuration with this state and this particular information on the tapes to this next state in one step, this next configuration in one step, in which the tapes will be pretty much the same, but they might just have changed at the places where the head positions are, and the head positions might have moved by plus or minus 1, and the state might have changed arbitrarily. But anyway, there's one step of computation that takes us from this configuration to this. So this is how we define the graph as an edge, directed edge from C to C prime, if and only if M can make one step of computation from C to C prime. And as last week I mentioned that the amount of information here in a configuration can be encoded by a string that's polynomial in the size of W. That's because we have a polynomial amount of space used in the computation as a whole running on W. We can own these input tapes, they can only be a total of P of the length of W, a total of that many different squares on the various tapes can have been used in the computation. So the whole state of the computation can be captured by capturing the state, the contents of those P applied to the length of W many squares, the contents of that many squares, plus the information about the head positions, and the head positions can only point to the space that's been used as well. So we had this last week, that so every configuration, that's not a good pen. Every configuration C can be encoded by a string, which I write as code of C, which can be just a string of bits, and its length is some constant. As I said last week, it's a bit awkward. This is a little c, this is a capital C for configuration. I'm using the same bad notation, C times P of the length of W. And this is going to be an important number here. So I'm going to write N for this number. P times P. So N. Okay, so we encode these configurations so that all the information about being in configuration is just coded by a sequence of bits. Now we do the very, very tedious bit, but because we've done it once for the Levin-Cook theorem, the Cook-Levin theorem, I'm not going to do it again. There are some hints about it in the lecture notes, but I might come back to it if there's a bit of time left at the end, but probably there won't be. It's very similar to the proof of the Cook-Levin theorem that the set is empty complete. So similar to the proof of Cook-Levin. We find a propositional formula, not yet a TQBF, but a propositional formula, or construct is a better word. Which I'm going to call the formula phi of the machine M on input W, which has 2 times C times the polynomial of, so this is the amount of, remember P of the size of W is the amount of space that the computation uses, C times that multiplied by a useful constant factor, and we're encoding everything in that many, that's n bits. We're going to use 2 times n variables here. So I'm going to call them U1 up to UN, U capital N, and V1 up to V capital N. And this propositional formula has 2 properties. The size of the formula is linear in this capital N. So the size of the formula is linear in the amount of space the machine uses. And the more interesting property is that this formula is going to encode the transition graph, the configuration graph, in the following sense. So the formula, when applied to a vector of Boolean values, 2 vectors of Boolean values. So here, A and B are both, each of them is both a sequence of n Boolean values. So I'm writing this to say, here we've got the vector of length n of Boolean values and another vector of length n of Boolean values. We're substituting the A vector for U1 up to UN, and the B as the truth values for these variables, and the B vector for V1 to B to Vn. But the idea here is that this formula is going to say, this vector encodes a configuration, this vector encodes a configuration, and this formula, so this formula is true if and only if these 2 vectors encode a configuration, and there is a directed edge from the one configuration to the other in the configuration graph. So it says, so this holds if and only if this formula is true for A and B, if and only if there exist configurations C and C prime such that vector A is the code of C as a string, vector B is the code of C prime as a string, and formula being true says also that there is a single step from C to C prime. And basically, what this formula does is it does things like whenever there's a transition in the Turing machine saying if the head is in a certain position and if the head sees the A character and they're in the state Q, then it checks. So if A is a sequence of bits that represents that information, then B is a sequence of bits that represents the information that basically all the information on all the tapes is the same, except that the new bits of tapes that needed to be overwritten by the single step have been overwritten in the encoding of B, and the heads have moved accordingly. So we have legitimately made a step of computation. But it's the same, we already did essentially the same things in the Evans theorem. We encoded each step of the computation using a propositional formula. It's the same thing going on here, but instead of talking explicitly about time in the variables, we're not having time, we're just looking at a single step at a time, and instead we use these two bit sequences of variables in order to say the encoding of these variables represent a configuration, these variables represent a configuration, and there is a single step between them. Okay, so there are a few more hints about how to construct this formula in the lecture notes. But I realize I don't have much time. So now what we do is we construct a quantified Boolean formula, such that psi I, in fact, a family of such things, such that the size of psi I is polynomial in N and I. And for two configurations, C and C prime, and psi I of the encoding of C and the encoding of C prime equals 1, if and only if there is a path from C to C prime of length 2 to the power of I. And let's put this up to the top. So what we really want So given the above, we have the following reduction from L to then have a reduction from the language we started in with, which is our NP-space language, L to the truth of quantified boolean formulas. And this reduction is given input W, construct the formula psi, the big N of U B as above. Then psi of N, if we plug in the start configuration and the accept configuration, this is going to be true if and only if there exists a path of length 2 to the n from the start configuration to the accept configuration. But because the number of configurations is bounded by 2 to the n, which was up there, so there are only 2 to the power of n possible configurations, according to the line at the top there. If there exists a path at all from start to accept where you can cut out any loops, and then there'll be a path that only goes through distinct states, so there must be a path of length 2 to the n. So this is simply if and only if there exists a path full stop of whatever length from start configuration to accept configuration. And this is if and only if, well, there's a path from start to accept, if and only if it's a non-deterministic Turing machine, if and only if the Turing machine accepts the language. So if it accepts the word, there's a non-deterministic Turing machine deciding L, so this is true if and only if W belongs to L. So there are a couple of things I glossed over here. Firstly, I'm saying the accept state, well, to make there to be the accept configuration, so to make there be just one accept configuration, we do the same thing we did last week, and we get the Turing machine, which we can do without loss of generality, to delete everything on its working tapes before it goes into the accept state. Secondly, I'm saying there's a path of length 2 to the n. That means we want it to be in an accept state at after exactly 2 to the n steps. So to allow that, we want to make sure it doesn't halt too soon. So we do the same thing we did in the proof of the Cook-Levin theorem, which is to add loops on the accept state. So when you get into an accept state, you stay in the accept state and you just idle there. Well, compute there one step at a time. And therefore, if there exists a path to the accept state, there'll be one of length exactly 2 to the n. So that's how we address those issues. The other main thing I haven't done is I haven't told you how to construct this quantified boolean formula psi I. But I'm afraid there's no time for that now. This is an important part of the proof, so we're going to begin with that next week. And I might, I put the notes online so you can have a look at that. That's the nice little bit of the proof, but I'm sorry I ran out of time. And I can't overrun because we've got the student presentation. Well, I have overrun already by 4 minutes, but I can't overrun more because we've got the student presentations. So we're going to have 6 minutes break now. I would like to take attendance here. I'd like you to also sign up and do the attendance online. But I also want to have my own record of attendance. So I'm sorry, you people on Zoom, but there isn't going to, the student presentations are not going to be broadcast on Zoom. So thank you for attending. I'm sorry if you couldn't see the whiteboard, but in any case, this is the best I can offer this year.
Anyway, I'm going to stop the recording now.